Welcome to the Deep Dive, where we unpack fascinating ideas and give you a shortcut to being truly well-informed.
Glad to be diving in.
So today we're starting with something that honestly sounds a bit wild. The idea that for centuries, motion itself, the very concept in Europe, was kind of stuck, frozen.
It really was.
Yeah.
Imagine a world where everyone, well, nearly everyone in intellectual circles truly believed an object only moves if you're actively pushing it, constantly.
It's hard to wrap your head around now, isn't it?
Absolutely. After Aristotle, especially, the understanding of motion just sort of ossified. It got tangled up in theological debates, sometimes seen as suspicious even. It wasn't just wrong, it was dogma.
Okay, so that's the backdrop. This deep dive, then, is about what our source text, the quiet reboot of motion thinkers, 1300-1450, calls a quiet reboot.
Right. Starting around 1300, lasting maybe 150 years, these folks, they were the unsung pioneers, laying tracks for Newton and Galileo centuries before they were even born.
And our mission here is to look at 4 key figures from this period, often overlooked, but they ask these, well, dangerous questions for their time.
Dangerous because they poked at that established dogma. And they really did start to get the gears turning again, quite literally in some cases.
Exactly. And as we explore what they did, challenging old ideas, drawing the first graphs, building these incredible machines, we'll tie it back to this framework we often use, motion theory.
Which, just as a quick reminder, views basically everything, the whole universe, as structured motion.
Mm-hmm.
Everything moving, vibrating, syncing up.
Like a cosmic dance creating reality. And these early thinkers, they were starting to hear the music, figure out the steps.
Mm-hmm. So let's paint that picture first. Before 1300, Europe is in this theological stasis, as the source calls it. Motion is discussed, sure, but often through the lens of God's will, divine purpose.
Not so much about, how a rock actually falls.
Precisely. Less empirical observation, more philosophical or theological argument.
And the shift wasn't some big bang, right? It was quiet.
Very quiet. It started with, everyday stuff.
Yeah.
New kinds of clocks being invented, people noticing how weights behave when they drop, sketching things out, tangible things.
And underpinning it all was this genuinely risky question they started asking, even whispering maybe.
What if motion doesn't just stop on its own?
Seems simple to us, but back then...
Oh, it flew in the face of centuries of Aristotelian thought. The idea that motion needed that constant push.
Which brings us to our first figure, Jean Buridan, French priest, philosopher around 1300 to 1358.
Right, and Buridan is one of the first, certainly one of the most articulate, to really take on Aristotle directly on this point. Aristotle's model, stop pushing, it stops moving, done.
But Buridan looked around and thought, well, hang on.
Yeah, he saw things. An arrow keeps flying after it leaves the bowstring. A spinning top keeps spinning. That didn't fit the old model.
So what was his alternative?
He proposed this idea of an internal impetus, something imparted to the object that keeps it going. He actually wrote, after the projector has ceased to push, the object is still moved by the impetus given to it.
Impetus. It's not quite inertia, but it's getting awfully close, isn't it?
It's the direct ancestor. Centuries before Newton formalized inertia, the idea that motion continues unless something else stops it. Buridan had this foundational concept.
So how does that initial spark connect with motion theory?
It's fundamental. Buridan was seeing, maybe intuitively, what motion theory frames explicitly. Motion persists. It resolves. It continues its pattern, its loop, until something disrupts it, what we'd call a loop conflict.
So motion is naturally self-sustaining until interfered with.
Exactly. Buridan was sensing that deep truth. He really did, as the source says, light the fuse.
Okay, so Buridan starts questioning the why of continued motion. Then comes Nicole Oresme, another French thinker, a bishop, lived about 1320 to 1382.
And Oresme's contribution is fascinating because he shifts from just talking about motion to, well, drawing it.
Drawing motion. How does that work?
He started creating what we'd instantly recognize today as graphs, plotting, say, speed against time. He was doing this centuries before Descartes gets the credit for analytic geometry.
Wow. So he'd use shapes like rectangles and triangles.
Yes, to represent velocity over time. He showed how speed could change, depicting uniform acceleration, for instance, using geometry to visualize motion's qualities.
And the source mentions he was essentially describing area under the curve.
He was. It's astonishing. He was using geometric area to represent the distance traveled during accelerated motion. That's a core concept in calculus in years before Newton and Leibniz.
Just incredible. So for motion theory, what's the significance of Oresme drawing these graphs?
He gave motion a rhythm, a quantifiable structure over time. He used shape, symmetry, structure to track how motion changed. This is the birth of what motion theory calls dimensional sync tracking.
Meaning tracking how movement unfolds across dimensions like time and space.
Exactly. Moving beyond just it moves to how it moves, how fast, how that speed changes, and representing it visually, mathematically. A huge step toward seeing motion as this resolvable rhythm across intervals.
From abstract ideas and visual graphs, we move to something very physical. Richard of Wallingford, an English monk, mathematician, roughly 1292 to 1336.
Yes, Wallingford wasn't primarily a theorist. He was a builder, an incredible engineer for his time.
And he built a clock, but not just any clock.
Not just any clock, no. He constructed one of the earliest, most complex astronomical clocks in Europe, the Albion.
Albion, what did it do?
It was designed to track the movements of the sun, the moon, potentially other celestial bodies. It used this intricate system of gears, weights, wheels. It could even predict eclipses, lunar phases.
Whoa. So it wasn't just telling you the hour.
Not at all. The source calls it a physical embodiment of motion cycles encoded in machine logic. It was basically a mechanical model of cosmic rhythms.
So modeling the heavens in brass and iron, what's the deeper meaning there, connecting back to motion?
Wallingford was, in effect, recreating cosmic synchronization. He was translating these vast, observed planetary motions into what motion theory might call recursive gear feedback.
Recursive gear feedback, meaning
Meaning the turning of one part drives another, which drives another, in these precise repeating cycles that mirror the celestial cycles. It's taking the abstract idea of heavenly motion and making it tangible, predictable, mechanical. A loop mimicking a bigger loop.
making the invisible visible and mechanical.
Yeah.
Fascinating. And building directly on that, we have Giovanni Dondi, an Italian living around 1330 to 1388.
Yes, Dondi took Wallingford's kind of concept and just ran with it, elevated it significantly.
The masterpiece was the astrarium, right?
The astrarium, an absolutely stunning piece of mechanical engineering. It was a model of the solar system as known then, with 7 intricate dials, one for each planet, including the sun and moon. It took him, over a decade to build?
Over 10 years. And like the Albion, it wasn't just about time.
No, it was about simulating planetary rhythm. The gears were meticulously designed and synchronized to reproduce the complex, non-uniform segments of the planets, according to Ptolemaic astronomy.
So a working physical simulation of the solar system on your desk, basically. How does that fit into the motion theory perspective?
Dondi quite literally built structured motion into metal. It's a perfect example of what motion theory calls motion encoding. He created a physical loop stack.
A loop stack?
Yeah, think of it as layers of recursive motion. Each planet's orbit is a loop, represented by gears, and these loops are nested and interlinked. It's showing that complex motion, like orbits, can be broken down and recreated through synchronized, repeating structured patterns. Whether it's gears or gravity, it's about encoding motion.
It's really quite amazing when you put them all together. Buridan questioning force, Oresme graphing change, Wallingford and Dondi building cosmic machines.
And like you said earlier, these guys don't usually get the big headlines in physics history. No statues, not typically front and center.
But their collective impact between, say, 1300 and 1450 was huge. They challenged dogma, visualized acceleration, mechanized the heavens, simulated orbits.
They really were this crucial transitional loop, weren't they? Moving thought from that static, almost purely theological view towards something dynamic, structured, observable.
So when Leonardo da Vinci shows up around 1452...
the stage was already partly set, the gears were turning, the thinking about motion had already started its reboot.
They weren't physicists like we think of them now, maybe not even philosophers in the old mold. They were rebooters.
Rebooters is a good word. Innovators asking new questions and using new tools, observation, math, mechanics.
So let's pull it all together through that lens of motion theory again. The core idea. Everything is structured, motion resolving through synchronization. How did these four fit?
Well, Buridan's impetus, his sense that motion sustains itself, that aligns perfectly with motion resolving, continuing its loop until something conflicts with it.
Right, motion keeps going unless stopped.
Oresme's graphs, showing motion as shapes changing over time. That's like seeing rhythm across nested loops, which motion theory says is how we perceive dimensionality. He's tracking the sync.
And Wallingford and Dondi with their clocks and the astrarium.
They physically built recursion. They showed that you could model reality, cosmic reality, with synchronized, repeating mechanical loops. For motion theory, it doesn't matter if it's brass gears or space-time fabric. It's all motion trying to find its rhythm, its sync.
So they weren't just making lucky guesses. They were observing, building, resolving truths about motion, even without our modern language.
Absolutely.
Yeah.
Their work belongs on that motion lineage. They were actively engaging, not just speculating.
Okay, so the final takeaway here. Motion didn't just suddenly reappear in the Renaissance.
No, not at all. It wasn't an explosion. It was a quiet ticking, a turning of gears, a plotting of lines, a slow, steady reboot.
These four thinkers, Buridan, Oresme, Wallingford, Dondi, they were like the first quiet beats of that Renaissance rhythm.
hmm From 1300 to 1450, this was the pre-sync era, when the West started to relearn how to track and conceptualize movement.
Motion never died, it just had to reboot.
They push the button.
So here's a thought to leave you with as we wrap up. How many other quiet reboots or silent syncs might be happening right now? In fields we don't pay much attention to, maybe.
Yeah, what seemingly small ideas or niche technologies or overlooked observations are building foundations today.
Foundations for the next big aha moments, the next revolutions in understanding that maybe we won't fully recognize for decades or even centuries. Something to think about.